Okay, so now we know what variables of state or thermodynamic variables are. We can let me say that we can classify them into two different categories. So there are extensive and intensive variables, and things like volume are extensive. And the reason why, what defines an extensive variable is that if I scale up my system or I downsize it, the volume, and for instance other things like the mass, are going to also change in the same proportion. So what is that I mean? Well, imagine I just have a system and it has some volume B, and if I decide to break my system into two pieces, the two pieces will have volume V1 and V2, and also will contain mass, say if you like M1 and M2, the total mass is M, and things are such that volume 1 plus volume 2 equals the total volume, and the mass 1 plus the mass 2 equals the total mass. So this is what I mean by extensive property. It scales in the same way that the system scales. And intensive variables, on the contrary, are locally defined. Okay, so they are defined at every single point of the system. For instance, when you see the weather report and forecasts and so on, you know there are maps of pressure, and you know the pressure has a different value in different places or even in different instants of time if you are in a system like the atmosphere, which is out of thermodynamic equilibrium. But we don't know what thermodynamic equilibrium is yet, and we are going to talk about it now. So let's just write it down. Thermodynamic, just write it, dynamic equilibrium. So for this, equilibrium. So for this, let me use my mug of coffee as a prop. I've been drinking coffee or sipping coffee during this time, and when I started, this mug was freshly made and it was warm. It felt warm to the touch, but now it feels colder. And this warm and cold are physical sensations, outputs of the sense of touch, but there's something, if you like, quantifiable about it. It's not really the case, but you could argue that you can order objects in terms of their degree of warmth just by touching them with your hand. You can, to some degree, objectively determine what things are colder than others. Okay, so imagine I do this experiment with my coffee. No, so what I want to do is to record the degree of warmth of the coffee as a function of time in some arbitrary units that I'm going to make up, because warmth is not a physical property at all, okay? But just for the sake of this example, let's just quantify warmth here and time. And I know, freshly made my coffee, warmth is high, it feels hot, and then 5 minutes later it feels less hot, and 5 minutes later it feels even less hot, and so on and so forth. And at some point, however, I will see that the warmth has reached a stationary state. Okay, so the feature here is that there is some stationary state. This state is stable because I don't expect that after this happens, I don't expect the warmth of my coffee to go up suddenly or to suddenly start going down again. So it's stable. And also, if I am to look into the coffee carefully, I will see that if I touch the bottom of the mug, it feels equally warm as the sides. If I dip my finger into it, everything feels exactly the same in terms of warmth. I know that other macroscopic properties that I could measure and I could investigate will also feel homogeneous. For instance, the density. There's no density gradients. There's no convection of coffee inside of the mug. Everything is sitting still and uniform. So this homogeneity is another feature, well, homogeneous in this case, right? Homogeneous. So these three features, if you add them together, equals what I call thermodynamic equilibrium, okay? And in particular, to be more precise about this homogeneous, what I mean is that all intensive state variables of your thermodynamic system adopt a constant value throughout the system. So when this happens, you can tell that you are properly in thermodynamic equilibrium, And what has happened from a more abstract point of view, if you like, is that you had a system which was the coffee A, and you put it in somehow in contact with system B. System B is huge in this case, it's the air in this room, because the Mac is uncovered, there's no lid on it, and the coffee, the surface of the coffee, is in direct contact with the air around it. So this means that these two systems are able to somehow change their degree of warmth, and they arrive to a state of equilibrium. And this state of equilibrium is a state of mutual equilibrium. So this is the notion I wanted to put. There is a when you put together different systems, they attain a joint equilibrium state. Okay. So now we're ready to introduce the first law of thermodynamics that we're going to see, which is not number 1 but number 0. That's the 0th law of thermodynamics. And the 0th law of thermodynamics, you can also find this under the heading of Planck's formulation of the 0th law. It says the following. So imagine I have a system A here, yes? Well, actually, imagine I have a system B here. And I put it in thermal contact, and I'm not describing precisely what thermal contact is, just the type of contact that happens between my coffee and the air. Okay, I will define this more carefully later. I put them in thermal contact, and maybe there is some transient dynamics like I described. Perhaps if you touch system B and system A periodically in time, you will find that their degree of warmth is going to change over time, but at some point it's going to become stationary, stable, and homogeneous. And then I can say that A and B are in thermodynamic equilibrium with one another. So if I now take system A and I put it in, again, thermal contact with a different system C, which is somewhere else, far away, and I see no change whatsoever. So I see that when I establish thermal contact between the two, there's no change in the warmth, there's no change in any measurable physical property that I can access from the macroscopic perspective. Then I can claim for sure that if I were to put directly the two remote systems B and C directly in thermal contact with one another, also nothing would happen. Okay, so this is what the 0th law of thermodynamics tells you, is that being in thermodynamic equilibrium with another system is a transitive relationship. So if A is in thermodynamic equilibrium with B, and at the same time A is in thermodynamic equilibrium with C, it means that B and C necessarily are in thermal equilibrium with one another.